Hi guys, so in this video we're going to be looking at the D flip-flop. In the previous lecture we were able to cover the D latch, look at how it helps us overcome some problems we had when facing with the SR latch. But in this video we're going to move a step higher than that. Look at the D flip-flop, its advantages, its schematics, its function table, and even get to draw some timing diagrams for it. Okay, so the first thing we have to cover is why the D latch isn't so perfect in the first place, even though it's literally solved all the problems you had when dealing with the SR latch. Okay, so let's draw a D latch, nor implemented. So remember, it's the same setup you would have for an SR latch. 2 NOR gates, outputs tied together. Okay, then I have to eyeball this. Oh, okay, this way is better. So these are 2 NAND gates, and remember these inputs are tied together to form what we called our enable signal, E. Okay, and then the real magic of the D latch was bringing this guy down all the way here and inverting it. Exactly. Okay, so this is the circuit diagram for the D latch. Remember, it really looks like it does for an SR latch. So that means this sort of plays the role of resets, and this would be for, okay, that should be these lines, not the gates. Okay, and this would be for sets, and this is enable. So this is what we had for the D latch, and the problem this helped us overcome was the invalid state of 1 and 1 when we had the SR latch. Okay, because with the D latch now, because of this inverter, because we have one input and because we have an inverter, that means these two guys can never be the same thing, which means that the input states 0 and 0. Let me put that on the table. That means the states 0 and 0 and 1 and 1 can't happen in the D latch. They're always going to be opposites. So the only states we can have are 1 and 1 1. Okay, so that's on this line, on the S line, on the R line. Okay, would be 1 and 0 and 0 and 1. So remember we said that we're tying these guys together with an AND gate so that our enable signal comes on and allows our circuits to function. So as long as, okay, so let's draw another table here. So as long as our enable is off, then nothing we do has any effects on our output. Remember we established that. So enable D, and let's call this Q. As long as enable is off, either D is 0 or 1, there's going to be no change on our output. But once our enable comes on, then Q follows D. Okay, we're able to establish that. So now we run into another problem. Remember the D latch helped us solve the problem of the SR latch. Now we come to see why the D latch isn't even so perfect in the first place. The problem we have is that what if we now need to take periodic samples of our data? What if we need to know the state of our data every, let's say, 5 seconds? Okay, so 5, 5, 5, 5. So there's a 5-second gap between signals. I want to sample it at that time. Does that mean that we'll have to physically press or turn on our enable signal, then change our data, which making that non-automated, having to turn on your enable before turning on your data, or while doing that, is going to introduce a lot of plus minus errors in between two of these. That's going to make your reading less accurate. Remember we said that the D latch is level triggered. Okay, so that means while we're drawing the diagram for the D latch, as long as D is high, so let's do something like that quickly. So let's say this is our enable signal, low, and it comes high this way, low for a bit, high. Okay, so remember we said that as long as our enable is high. So let's say this would be 0, this would be 1. Okay, so this is just a sneak peek sort of into what a timing diagram looks like. So this is our enable signal E. So once this is high, so this is low, so it's high for this entire period, it's low, and it's high for this entire period, and it's low for the rest of this. So if our data, okay, so let's see if, let me draw for the data too. Let's say D comes on, comes down, comes on, let's say it comes down here. Okay, so let's see if we can figure out, so let's say 1, 0. Let's see if we can figure out the timing diagram for Q. All right, so as long as our enable is 0, so let me sort of draw this down, then Q cannot take a reading. Remember, that's what we said. But once E comes on, our circuit looks at Q. So E coming on is what allows us to look at Q and say, all right, check this value now. And we see that it is high, so we come high. So we check, is enable still on? Yes, enable is still high. So we follow this drop down exactly as it is here. Is enable still high? It is. So you follow it down, you come up exactly, and you keep going. So once enable turns off, you maintain the state, because that really doesn't, you can't take a reading until enable comes high again, and then you can follow your reading. So we'll get into this later on, but this is just one of the issues we had with the D latch, meaning that for the period enable is high, my data could flip between high and low for this entire period, which gives me unstable readings. So that's one of the things we're going to encounter. So how do we solve this problem of our D changing multiple times within a reading? Because my enable could be high for 2 seconds, and let's say at 0.2 my D is 1, at 1.6 seconds my D goes off, and at 1.9 seconds my D comes high again. Okay, so these are 3 different readings in one time period. So let's say in the 2 seconds that my enable was high. So that's something that we really don't like when dealing with sequential circuits. So we're going to see how the D flip-flop helps us to eliminate this problem. So the big idea behind the D flip-flop, the circuit diagram is the same thing as the D latch. But what changes now, the real trick is going to be with our enable signal. So let's draw this and see what it will look like. So we have an AND gate, as we always have. No implementation. Comes out. Feedback. Okay. This comes back to the output of not Q. Second NAND gates. So these two form our steering circuits. As another name for this part of the circuit diagram. So we take this out. Okay. Tie them down. And then we negate. Alright. So this is D. This is Q. And this is not Q. So the real solution to this lies in what we feed into what would be our enable. So remember before, this input is our enable, or was our enable. So what we're going to do now is to change this from an enable signal to CLK, what you call the clock signal. So usually you can see it as C, or you can see it as, you can see it as C, you can see it as CLK, or you can even just see it as something this way. Or even sometimes if they're drawing they could draw like a circle and do something this way. So either way, you're dealing with a square wave input. So remember the video where we talked about important concepts in sequential circuits. Remember we handled different types of triggering, level triggering and edge triggering. So with D latches, the trigger we had was edge triggering, meaning that so long as enable was high, so once enable was high, everything counted. But now we're going to deal with edge triggering, which means we're going to be looking at the edge of our clock signal. So what really is the clock signal? So the clock signal is a very important concept when dealing with sequential logic and really electronic circuits. A clock signal is a periodic square wave with a known period and a known frequency. Okay? So you're low for a while, high for a while, low for a while, high for a while, low for a while, high for a while, and so on and so forth. So this is now the very important building block. It's like a conductor or a referee for a circuit. So because you have a known signal controlling when things do and do not happen, we're able to take only one instance of a reading and not have multiple changes over one occurrence. So a clock signal, usually could be measured in, you could have 8 megahertz, 16 megahertz, and so on and so forth. All right, you can see them usually. The circuit symbol looks something like this, okay? And they're actually usually real life crystals. So it's a really fun concept. So with this clock signal now, you can see that, with enable, you had to physically press a button. You could physically turn on the input, so it could be high for a while. As long as you turn it on, then some low. So it was really up to you. So the real way, an example we can use to see, pardon me, an example we can use to see the real advantage of this is to imagine the best way to implement a doorbell. Okay, so I'm going to leave this as it is and see if I can do this example quickly. So we have two ways theoretically to implement a doorbell. So the first one is that the doorbell rings as long as you're pressing it. Okay, so let's write this. So it rings as long as pressed. Okay, so let's say you walk into the doorbell and you see the door with the doorbell. So as long as you press it, okay, then the sound comes out, right? So if I hold it for 10 seconds, then the doorbell rings for 10 seconds. If I hold it for 5, then it rings for 5. If I hold it for 20 seconds, it rings for 20 seconds. If I hold it for a minute, it rings for the full minute. But then the second, another way to implement the doorbell is that it rings for, so let's say it rings for 10 seconds once pressed. Okay, so we have the same scenario. You walk into the doorbell, you see the door, and you press it. However, the important thing with this second implementation of the doorbell is that it notices when do I go from not being pressed to pressed. Okay, so we're dealing with binary now. If we call not being pressed is 0 and being pressed 1, then that means we're going on the rising edge of this signal. Okay, so these are really cool implementations of logic, Boolean logic. So this second doorbell rings for 10 seconds once it's been pressed. So you walk in and you press the button and it rings for 10 seconds. So if you're pressing the doorbell in between those 10 seconds that is ringing, it is not going to notice your inputs. All right. And then we can see usually from experience that this does far better than this example. With energy conservation, it's easier to code and it's more appealing basically when dealing with home security, because I'd rather have this than someone pressing my doorbell all the time to sort of take me off. So that's the issue. That's the good thing actually when dealing with clock signals. So now instead of looking for the entire period where the clock is, when my enable is high, I'm looking at when does my clock signal change. All right. So recall there are two ways to okay, there are two edges to handle it. So 2 types of edge triggering. Okay. The first one is positive, and the second is negative edge triggering. I'll explain this in right now actually. So let's look at this. So now instead of enable going from, instead of us noticing when the enable is high, we're now looking at, so let's implement the positive edge triggering first. So positive edge triggering. Okay. positive edge triggering. So let's see. This is a logic 0, and this high part is a logic 1. So that means this transition over here, going from a 0 to 1, is a positive edge trigger. Is a positive edge. Okay? It's high for this period. Going from 1 to 0 is the negative edge, a falling edge. Okay? It's low for this period. So I could write 0. It's high here. Is 0. Then since it's going from 0 to 1, then this is my positive edge. Okay? This is falling. It's going from 0 to 1. This is my positive edge. It's falling. It's going from 0 to 1. This is my positive edge. So like so on and so forth. Right? So what now happens now is, so let's take this down. And let's see what happens when we make our data change during this period. So let's draw for data. So we really don't have to do this. Let's randomly change between 0 and 1. Okay. High for a while. Low. High, low. Let's say low for a while. Okay. Because data really could change anyhow. But what we want to do is see our Q is our copier. Is meant to copy the output D, but it's not without limitations. It's only copying D on the rising edge. Okay. Remember, we're doing the positive edge triggering in this case. So let's see. So 0, 1. 0 and 1. So we start off low. We start off being low, as we would normal circuits. So look, we're on the rising edge now. So once we're going on the rising edge, we look at our data signal. Okay. So what the rising edge does is help us, is a pointer to check our data. Okay. So you're maintaining previous state. If I see a rising edge, check my data and maintain to the next clock cycle. Okay. It's important to know that the entire clock cycle is the full up down, false cycle. Okay. So the full period up and the full period down, this is my duty cycle. It's my entire pulse, right? So the same way sinusoidally, this is the full period. Then, this is the full digital. This is the full analog period. Okay, this is the full digital period. So maintain previous states. If I see a rising edge, copy my data to the next rising edge. So that's the logic we're going to use. So we have a rising edge over here. Come, check my data. Data is low. So I ignore this and stay low to the next rising edge. So you can take a look and see that our data D changes from 0 to 1 in this period. But you look closely and see that this is not changing at the rising edge of our signal. So there's really nothing our Q can do. So it maintains its state until the next rising edge. So it just gives us more control over our data. So we've encountered another rising edge, and we see that this is still high. Okay. So perhaps only with a small gap. Okay. So we see that this is still high at the rising edge. So we can remember, maintain previous states. If you see a rising edge, check my data, copy my data, maintain that state to the next rising edge. So I see that my D is high on this rising edge. So I come high, and I maintain my highness until the next rising edge. So you can see that D comes low within this period, but since it is not at the rising edge, it is outside the observable period of our output Q. Cool. On this rising edge, my data D is high, maintain my highness. On this rising edge, okay, let's sort of keep this down. Okay. So we take this down, 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 and take this down. So it usually helps to do, these dotted lines before you draw anything on your circuits, so that you are safe. You spared the error of mistaking the falling edge for a rising edge, and so you can actually also have visible boundaries on how it's done. Okay, so on this rising edge, my data D is high, so I don't even care what's happening. Maintain my highness to the next state. So you look at it, D falls within this period too, but it's outside the sampling period of this. Okay, so that really doesn't bother us. On this rising edge, my data D is high, and I stay high throughout. So come and look at this rising edge. What happens now? My data D is low, so I come down and I stay low to the next clock cycle. It's high, so I stay high to the next clock cycle. It comes up exactly at this rising edge, so I stay high. It's low over here, so I come low. Okay, so it's like this is falling. Okay, what do we say for this guy? So let's say it's high for a tiny period after this. Okay, so we come high and we maintain high, and this is low here, and this is low here. So we can now see that even though D is the same as, because the formula for, you can express the D latch or the D flip-flop as D equals Q next. Okay, the current data state is going to be Q on the next time around. So you can see that although Q is meant to copy D, our timing diagrams are not the same because we're using edge triggering. So you can literally think about it as a camera. You have a changing scene, you have changing scenarios. But once your clock goes from 0 to 1, you take a snapshot of what happens. You take an instant snapshot of what happens. So you're left with an array of what happens at particular points in time. Okay, so although I'm handling moving images, with D I'm handling changing periods, right? My clock allows me to take snapshots of my data at particular points. So instead of one long video copying this, I have a series of pictures. Okay, I have a series of images that I can use to reconstruct what happens since they are periodically spaced. Cool. So you can see I'm dealing with the rising edge. So it's very simple. Usually you draw this down to help you maintain the error and to keep it till the next cycle. So it starts low, we're resuming normally low. On this rising edge, D stays low. So I stay low to the next cycle, even though D comes up. So it's now possible for certain inputs to be out of range. Remember the doorbell example we gave? As long as I press the doorbell during the period after I've already pressed it, and within the 10 seconds it's still ringing, nothing is going to happen. So this is the big idea when handling the flip-flops. It's exactly the same thing that's going to happen when you're doing the negative edge triggering. You're just going to do your falling arrow on the falling edge of your signal. So that's falling from a 1 to a 0. So usually for the same circuit or for the same change in D, if we use the same signal we did for this positive edge triggering example, we may not end up with the same thing, right? Since we're sampling at different periods. But overall, since it's negative edge triggering, we're still going to be correct in a way. So just so we're absolutely certain of what happens in negative edge triggering, I'm just going to draw a really quick clock. Okay. Low, high, low, high, low, high. Clock signals are usually more regular better drawn than these. Okay, so now we're handling negative edge triggering. Okay, so this is going to be negative edge triggering. Negative edge triggered. Okay, so we're going to look at it. When am I falling from a 1 to a 0? Okay, going down, going down, going down, going down, and we're going down. And remember I said we can usually, so do this to help us with our periods, our clock periods, more specifically. Okay, so let's stop here for time. So let's really mess around with a data signal. Okay. Up, down, up, down, psych, and stay down throughout. So now let's really do this quickly. We're looking at our output queue, or watching our output queue. Okay, remember this is still, this is still D. Okay, our data, and we're looking at our output queue. So let's look at what's happening. We stay low to the first pulse. So this is our first falling edge. Remember, maintain states on the falling edge, check data D, copy data D. So D is high, so I'm going to stay high until the next clock cycle. I really don't have to check what's going on. So you can see that we have this data bump here, okay? And I'm going from, this is random data spike here from high to low, but that gets ignored on our output queue, okay? So this is now an advantage, because usually when dealing with real life signals, real life registers, you've got noise, you've got interference, EMI, electromagnetic interference. So having specific intervals helps you to avoid accidentally capturing that in your data. So on this next clock cycle, maintain states. On the next cycle, look at your data, copy the states. So D is still high, stay high to the next state, ignoring this drop. Next pulse, copy D. So D comes low to the next cycle, D stays low, D comes high, D comes low. So like so, and as so on and so forth. So this is really what happens when we're dealing with D flip-flops, and usually you would hardly encounter any sequential circuit example that does not deal with clock inputs. They are more regular, they are more reliable than physical enable signals. Level triggering sets you up for a lot of disaster. So this is the setup in handling D latches and D flip-flops. We'll likely look at more complex timing diagram examples, compare the D latch and D flip-flop. But if we don't, we'll now get over to the JK flip-flop, which is closer to this. Is a build-up from this, right? How the clock inputs is now able to change and make my flip-flop more reliable, completely eliminating the invalid 1-1 states, making me able to maintain my state, to toggle between states, to do my normal sets and resets functions. So sequential circuits, it's a really fun endeavor. Hope we've been able to cover this properly, and I'll see you in the next video.